Right, guys. Today, in this presentation, we are continuing with. Actually, we want to get to a situation where we can get new derivatives, not necessarily from using the limit of the incremental quotient, but using something else. What we need actually at this stage, I need to explain to you what we mean by an implicit and what we mean by an explicit function. Then our target actually is to learn how to differentiate explicit functions, then from explicit function try to derive other derivatives, which maybe is a bit tedious to use the limit of the incremental quotient. So let's start this way. There we've got implicit and explicit. Now, explicit, in simple terms, something is explicit when something is actually like self-explaining. So like if you've got a function like, how to use this in maths? If you've got a function like 2x squared plus x minus 4. Because this function is defined by this expression, it's very clear to everybody how to compute the values of y. Remember, functions, we plot them on systems of axis, xy system of axis, or on the xy plane. So then this one tells you exactly that if you input x, how are you going to compute your value of y? Then you can draw maybe the graph for that. But this is what you can call explicit. Let's write there explicit. But on the other hand, sometimes you find yourself given a function this way, 3x minus 4y equals to 6. In this situation, we must still have in mind that we're dealing with a function of x altogether. But this function is not given explicitly as that one. It doesn't immediately give a suggestion how you are going to compute what the values of y. So this is when you describe the function given this way. That is implicit. But now, about this one, this is 3x minus 4y equals to 6. The good thing about this one, it is actually possible to take this thing to an explicit form. What do? You can just do some equivalent transformation here. Subtract 3 on both sides. You're going to get 4y equals to minus 3x plus 6. And then if you want y, you divide both sides by 4. You get 3 over 4x plus 6 over 4. Now, at this stage, the function is explicit altogether. So then, if all the functions could be done this way, that you get it implicit, you can take it to explicit, then there's no need to do this discussion. The problem is, we have situations whereby, let's say you've got something like this, x, let's say 3x plus y equals to, let's say, sine of y. Again, in this situation, we're dealing with the function x of y, which can be plotted on a system of coordinates, and then, which raises the question now, if the function is given this way implicitly, the question would be, how could we get the rate of change of the function with respect to x? In other words, we're saying, how could we get the derivative of a function which is given implicitly? Given that in this situation, if you manage to make y subject to the formula without having y on the other side of the equation, then you're performing the miracle. It's impossible. You cannot have this function as y equals 2, and you've got an expression here which solely depends on x, meaning that the function has been taken to its explicit form. It's not possible. So then, we then leave the function as it is, and then start asking, how can we differentiate that function in the way that we can manage to get what? Dy dx. Do you understand what we're dealing with now? Do you understand what is it we have to understand? Okay, so now let's move and see whether I can do it. Let's say implicit function, implicit differentiation. Now, let's say we've got a function here, y squared plus, let's say, sine of y equals to x squared. Again, this function is not possible to express as an explicit function. But having this function as it is, what you must understand, what must be at the back of our mind, in the background there, even if you don't write it explicitly, this function is actually a function y, a function of x, which is being squared plus a function sine, which is actually acting on a function y of x. All that gives us x squared. Let's say that's that. Altogether, that's what it is. So wherever we're looking at y, we must understand that is a function of x. Then it makes sense then to talk of dy dx, because this y we are having is a function of x. The only thing we don't have an expression which says y equals to something something. Altogether. But that does not stop us, not having y equals to something, that does not stop us to determine this kind of a derivative. This is what I'm trying to explain to you. Altogether. Now let's take this one as an example. We're having y squared plus sine y equals to x squared. Now, when we're going to find dy dx here, what do we need to do actually? I'll write this thing this way. I'll say dy dx. I call that a differential operator. When I see this thing tells me I'm going to differentiate whatever I put after this operator. So now, what are we going to differentiate here? We're going to differentiate y squared plus sine y equals to x squared, and that. What I mean there, is that I'm going to differentiate this equation throughout, from the left-hand side throughout to right-hand side. So what exactly are we going to do? We're going to come to this term and check what kind of a function do we have here, and differentiate it according to the rules which we have already learned. And when I come here, I know that this is a sine, but it's a sine acting on a function y. Then I differentiate this according to the rules which you differentiate. Which rule do you think we're going to need here? We've got power rule, we've got chain rule, we've got sum rule, we've got a rule which deals with the quotient, constant multiplied by a function. What do you think we're going to use here? I'll remind you. We're going to use chain rule. Okay, thanks. Somebody is saying chain rule. What are we going to do? We're going to call upon the immediate derivative of sine. But any function you differentiate, you must call upon its immediate derivative and then multiply by the derivative of the argument. Immediate derivative, I mean those things which you know how to deal with x to the power n. The immediate derivative is n x to the power n minus 1. Isn't it? But what if there you are having sine to the power n? You must say n down n minus 1 multiplied by the derivative of the argument. Altogether. That's what I'm saying there. So that's what I'm going to do. Then here, what I'm going to think we're going to need here. Sorry? Power rule. Only power rule. Power rule and chain rule. Because remember, the power function is acting on a function of x. So I'm going to apply the power and then multiply by the derivative of the argument. Understand? Then here we're only going to need power rule, simple x, because these are the powers of x. It's like we're dealing with a term in a polynomial. That's clear, isn't it? Okay. Now let's do the noise I've been making now. Let's implement the noise I've been making. We're going to say this is equivalent to saying 2y 2 minus 1. What is that? What am I doing here? What have I implemented here so far? Power rule. So multiplied by the derivative of the argument. The leading function is the power function. The argument is y. So it will multiply by the derivative of y with respect to x. It has been explained there that y is a function of x. So what have I done here? I've done almost everything. I've differentiated power. I've differentiated the argument of power. I'm done. Plus, when I come here, I call upon the immediate derivative of sine. What is it? Cos. So say cos, retain the argument, but multiply by the derivative of argument. Who can tell me what to write here? Come again? dy dx. Good. That's exactly what we should do. dy dx. Then equals to right hand side here is x squared, where I'm going to apply the power rule, which says 2 to x 2 minus 1. Though don't write this, precisely what we're doing there, we'll say dx dx. Like as usual, we don't write this. We know. But the reason why I'm writing this is because I want to emphasize, I really want to emphasize that even if you don't write it, it must be somewhere there in the background that there is the derivative of argument. In this case, it's the simplest derivative, which is going to be 1. Then you don't write it because 1 comes, any other number is that same number. It doesn't change it. So now what do we have now? What we have here now, we've got dy dx, dy dx. We're actually looking for dy dx. So which means now we've got an equation which is given in terms of dy dx. What we need to do is to make dy dx subject of the formula. Now, what you can do now here, since we've got this equation which has got written in terms of dy dx, the task is to make dy dx subject to the formula. So let's simplify by putting dy dx here as a common factor and writing this as 2y plus cos y, closing brackets here, and writing this as 2x, just as 2x. That is simple. Then the next thing, it will divide both sides by the bracket. So I'll just write here, divide both sides by the bracket. So if you do that, we then get to a point where we're going to be able to say dy dx is equals to 2x divided by 2y plus cosine y. Do you get that? Okay. Any question that far? Anything you think you don't understand? Is everything clear? Are you sure? Okay. So now let's take maybe one more example. One more example. Then we'll move forward. Okay, let's say, let's call this example number 1. This example, I'll just say example 1. Let's get here example number 2. Let's have example number 2 here. Let's say now we've got e to the power y plus y equals to sine x squared. But what you keep in our mind is the chain rule. The chain rule tells us that once we're differentiating a function, the function, we've got a leading function, we've got an argument can also be a function. So the route we follow, we differentiate the leading function multiplied by the derivative of the argument. So now, what is the solution to this one? First of all, we don't need to lose sight of the fact that we're looking for dy dx. Even if we don't write it like I'm writing it there, because I'm teaching here, I've got to write, I've got to highlight exactly what you should focus your attention on. So even if you don't write it, but you must know what you should focus your attention on. So in this expression, we're looking for dy dx. You know the chain rule, you know power rule. So let's differentiate each and every term like we did before. I'm now not going to write that d like the way I wrote it there. What I mean is, I'm not going to write that d dx. I'm just going to differentiate, as I know that I need to differentiate each and every term one by one. So differentiating here, we know the exponential function, we established that whenever you differentiate exponential function, it comes back exactly as it is. So like any other function, if this is its derivative, it will come multiplied by the derivative of its argument. But we don't really know how y is defined. So we just put a placeholder there for dy dx. Are we there, guys? Then we come here plus this side, we've got y. Again, we don't know how y is defined, we just put a placeholder dy dx. Equals, we come this side, we've got a function sine. So we call upon its immediate derivative, which is cos. We retain the argument. We always retain the argument. We keep the same argument as the function which was given. Is that clear to everybody? Okay. Then we multiply by the derivative of the argument. Then which could be 2x. If we continue there, we're going to be multiplying by 1, which will be the derivative of the argument of the power function, which is x squared. But like I said before, we don't normally take this because we must understand this there. So factorizing here, we get dy dx brackets e to the power y plus 1. Advice: whenever we've got something like this, we've got to multiply this function by the derivative argument. It's very easy, or it can, to somebody who's not very clear, it can suggest that you can multiply this x is there, then x cubed. This is outside the argument of what? Of cosine. Maybe sometimes we can even attempt to put brackets here that this is how far cosine x doesn't get to that side. Or the easiest way, I'll always advise you to write this before cos, then confusion is minimized. Are we getting that? Okay. Then after that, we make our dy dx, which is our target, subject to the formula by dividing both sides by what is in brackets. Then you get 2x cosine x squared all over ey plus 1. Then we're done. Now listen, I don't think we've practiced enough of product rule. That's what I gave you also as homework to practice. When we practice that enough, then we'll be able also to look at examples like this. Let me put it here as example number 3, but we're not going to do it because I want you to first of all get yourself immersed or get yourself very, very clear with the product rule and quotient rule. Then you can do things, implicit differentiations of functions like this. You can get here x squared multiplied by y plus sine x multiplied by y as the argument equals to 2xy plus 3x. I'm just going to make a comment on this one. I'm saying I'm not going to do this one now because I want you to be ready with your product rule and quotient rule and so on. But here I'm just talking about the product rule. You see, if you were to differentiate this term, you must understand that we've got a product of x squared and the function y of x. So then the product rule will be needed there. So that's why I'm saying that go and practice that. Then when you're ready, I can explain this one. Then when you come here, you will differentiate sign to get cos, but when you get to different derivative argument, again, you've got the product of the y and x. Then similarly, we've got the similar situation there, and so on. So this one I'm going to leave, and leave it as a motivation or good reason that you must really make sure that you immerse yourself in this product rule and quotient rule, practice it until it's very, very clear, because definitely you must expect this kind of exercises more than once. All together, guys? Okay. So I think after these two examples you've done, we are ready to move forward and talk about this. What are we talking about? We're saying here new derivatives using implicit differentiation. So I'm going to use implicit differentiation to derive new derivatives which we don't know. In this case, I'm talking about standard derivatives. When I say sine, cosine is the derivative of sine. It's just, those are immediate derivatives, those are standard derivatives. Those are things you're going to get on tables. But that's not all what you need to do serious differentiation. Altogether. But they are necessary because they form the foundation of the other challenging stuff as far as differentiation is concerned. Am I making myself clear? Okay. What am I talking about here? I'm talking about functions like this. Knowing that before we've dealt with an exponential function in natural base, and we know that the derivative here is exactly e to the power of x. But if I'm given the same function in a situation where it's e to the power x squared, then I know the derivative must follow what is done in chain rule. The function bounces back in part of the derivative, so it will bounce back as e to the power x squared. But according to chain rule, it will need to multiply by the derivative of the argument. Then I multiply there by 2x, then I'm done. Then the question is, what am I going to do here? Is it going to work the same? The reason why I'm using this strategy of using implicit differentiation here is because some of these functions, to use the incremental quotient is a bit challenging, it's tedious, and normally it's not worth to use a difficult method to understand a simple thing. It is easier to just use a simple method for people to understand a simple thing. If I had an alternative to not to use incremental quotient for this all the time, I could have used it. But now here, when you get to such a situation, it's really challenging. I'm avoiding it, but I'm avoiding it using the knowledge which we've already established. We know the techniques which we've learned to manipulate the new situation. Altogether, that is the strategy in life. First, with the new situation, you have something you know. Try to see if you can interpret the new situation in terms of what you know, and manipulate that way and see whether you get somewhere. The other situation here is to look at something like this, ln of x. And here I'm just going to put x greater than 0 to avoid putting the bars there. And also, later, we'll be able to also use this on something like this. But where are we going to start? I'm going to start here. Why am I starting here? I want to start here and exploit this derivative thoroughly to see whether it can give me some nice derivative of that. Let's see. And also, I'm going to use my theory of inverse functions. Now the question is, some people tells you, differentiate. Differentiate y is equals to ln of x. I know definitely, if I could put you this in the test tomorrow, you'll complain, but we haven't done this, but we haven't done this. But I'm telling you, if you think creatively, you can do this. So how are they going to do? Let's remember the fact that e to ln of x is equals to x. And the other thing we're bringing to this situation, we know this, we also know the derivative of e to the power of x. Those are things we bring into this situation. So how do you take it here? Let's apply ln on both sides here. And the other thing we have already now, from today, we have implicit differentiation. I like this. You know, every problem you solve in mathematics, and maybe in life generally, every problem you solve, you must try to check, what am I bringing to this situation? What knowledge am I bringing to this situation? What do I already know which relate to this situation? Those are the things which are going to push you forward. All together. So what do we know? We know this. 1. Let's use it here. E to the power of y equals to e to the power of ln x equals x. What are we looking for? Here, we're being asked to look for dy dx. That's the meaning of this differentiate. You say look for dy dx. But we don't know how to do it. But we want to use what we know. We know this, 1. We know that, 2. Let's now, from here, we're left with e to the power of y equals to x. Now, from here, I can say, I know implicit differentiation. If I know implicit differentiation, then let me differentiate this on both sides. If I differentiate this expression on both sides, the exponential function is going to bounce back exactly as it is. The only difference, for it to be a derivative, it will be multiplied by the derivative of its argument. But differentiating the right-hand side, I'll be differentiating x with respect to x. Let's call this the derivative of, who can give me that fancy word? Look where this x is coming from. That x which we are differentiating here originated from there. So we can call it the derivative of, who can tell me? What is x there? What position is playing there with respect to ln? What is it? It is the derivative of the argument of ln. Why is ln important? Ln is what we're looking for, its derivative. Altogether. Do you see that? That's why I'm emphasizing that. That's the derivative of ln. But now, here we have the y. What is y? Y is that ln we're talking about. So now, once we make this subject of formula, we've got the derivative of ln of x, which we're talking about. Is that clear to everyone? So let's make it subject of formula. We divide both sides by e to the power y. So if you divide both sides by e to the power y, we're going to get 1 here, which will end up giving us a dy dx. And if we divide here, we're going to have dx dx divided by e to the power e to the power y. Do you agree? Did you ever see e to the power y somewhere? Just check, move backwards and see whether somewhere we saw e to the power y. Did you? Did you see e to the power y somewhere along this working? Where? What is it? What is equal to? X. So which means here we precisely have got dx dx all over x. Let's look at something like this. Let's look at something like this. If I've got 3 over 5 all over 4. Is it the same thing as 1 over 4 multiplied by 3 over 5? I'm asking, I'm not sure. Is that the same thing? Is it the same thing? Are you sure? Yes or no? Is this 3 over 5 all over 4 the same thing as 1 over 4 times 3 over 5? Do you agree? Okay. Then if you agree, you should agree with me when I write this line as dy dx is equals to 1 over x multiplied by dx dx. Do you agree? Then I'm done. Then I'm done. I have something very beautiful here. The question has been solved. What was the question? The question was, what is the derivative of ln? And here is the answer. Listen to this. Put your pens down. Listen to this. The question is, what is the derivative of ln? There it is. What is the derivative of ln? Here is the answer. The derivative of ln is 1 over the argument of ln multiplied by the derivative of its argument. It doesn't get more difficult than that. Derivative of ln is 1 over the argument of ln multiplied by the derivative of the argument. Guys, this statement does not come simple, more difficult than saying the derivative of ln is always going to be 1 over its argument multiplied by the derivative of the argument. Now, let's look at an example. You know, I don't want to write in red. I prefer black. Example. Let's say we've got y equals to ln in brackets x squared plus 1. I've chosen carefully there that the argument is positive, x squared is positive plus 1 it will be positive, so that is fine. Now I want to differentiate. There's nothing I'm going to do except to mimic. I don't know whether you understand what I mean by mimicking. Have you ever seen a monkey? Huh? There are some monkeys, when you wipe your face, it wipes the face. You do this, you do that. That is really the behavior of a monkey. So I would like to actually behave like a monkey here and do this thing. So I write dy dx equals, I'm not even thinking, I'm just looking. I'm not going to do that because that is losing my message. That far, I've told whoever is marking this thing that I know how to differentiate ln. Before I make a mistake, instead of writing 2x, write 3x, then the person thinks I don't know. Altogether, that's the importance of writing steps very, very clear. At that stage, I've put down a statement that I'm clear in how to differentiate ln. Do you agree with me? Then I can now get inside here and carry out this operation, and then if I make a mistake, I'm sure of getting half a mark or half of the marks. Altogether, okay. Then 2x, the derivative of that, plus 0, which is 2x, over x squared plus 1. Let's call this example number 1. Then example number 2, it is said, show that dy dx is equals to cot x, where y is equals to ln of sine x. I put the bar there to emphasize that that should be positive. Then I'll give you 2 minutes. Push your pen against the paper and see whether you can do this. The first thing, strategy. Do you know cot? How is cot defined? How does it relate to sine? How does it relate? How does the derivative of ln works in order that it will give me something like this? Once you've got all those ideas organized properly, push the pen against the paper. Right, I'm giving you some 2 minutes or so to do that because it's not that challenging. Now, let's check. As we're discussing this, each individual must check what you've done or what you've been thinking about, whether it's correct or not wrong. First thing, from the first exercise, or even from the derivation of this thing, it tells us that a derivative of a ln is always in a rational form. In other words, it's something over something. Altogether, that's what the message we're giving there. So when we come to this example, that's what we see. We've got a ln there, the derivative is delivered in a rational form. Then when we come here, we're told that this could be the derivative of this kind of ln. Then we ask yourself, is this in rational expression like I would expect it to? Yes. What is this? This is cosine x over sine x. Already, when I look at this way, and I look at 1 over the argument multiplied by the derivative of the argument, I see that my chorus for differentiating that is correct. So what do? I come here and apply exactly the derivative of ln. We said it will always be 1 over the argument, which is going to be sine x, multiplied by the derivative of the argument, in this case the derivative of sine x, then which means I must know, in order for this derivative to be correct at the end of the day, I must know the derivative of that argument which is involved with the ln. But what is the derivative of sine? Then we come here, we write cos x over sine x. Then this is equals to cot x. Then I've shown what I was supposed to show. Are you happy? Are you happy or not happy? Okay. Right. We now know how to differentiate ln, natural base. I think we'll also be interested in learning how to differentiate log base A, which is not necessarily a natural base. But before we do that, let's look at how we could handle function y equals to a to the power of x. And remember, this function a here is considered to be greater than 0 and the a different from 1, because 1 is kind of an obvious case. Altogether. So what I'm going to do here, again, I'm going to use what I know. In this case, I'm actually going to exploit the derivative of ln, which I just learned today. What I'm going to do here, both sides here, I'm going to say ln of y equals to ln of a of x. Then I go back to the properties of ln, of logarithms. Then I say this is equals to x ln A. Be careful. This is not a function. This is a number. It's a constant. It's like I've got 2x. I can even write it this way. Ln of A, x. What I'm trying to do there, I'm trying to emphasize that this is a standalone number, which is a coefficient of x. It's actually a linear function. Y is equal to mx. And we said when we're dealing with linear functions, the derivatives we just extract. Remember that? So then now we've got this as ln of y. What did we say about the derivative of ln? We said 1 over the argument multiplied by the derivative of the argument. Then this will be equals to ln a. Is there anybody who doesn't understand why that is ln a? Do you all understand? The derivative here is ln a. Do you understand or not? Guys, I'm talking to you. If you don't understand, say no. If you understand, say yes. Do you understand or not? I'm not hearing anyone talking. You don't get it. If you don't get it, you don't understand that this is a number. Can you differentiate this? Do you have it to get dy? Dx there. What is dy dx? 2 or 2x? 2. This is what I'm saying. I said when you apply ln, this is a base, a number which is greater than 0. Sorry, here I want to say different from 1, which is greater than 0 and different from 1. This a is a number. So if I apply ln to a number, I get a number. So the number here could be a small number, it could be a big number. It's not a problem, but it's a coefficient of x. But I said the other day that whenever I got y is equals to m of x, that's plus c. That's a linear function. It's easy to determine the derivative that you just extract the gradient. So what is the gradient here? Is that. Is that making sense? Okay. Okay. Now what we need to do? We are targeting dy dx. That's what we mustn't lose sight of. So if we're targeting dy dx, we have to make this subject the formula. And the only way to make this subject the formula in this case is to multiply both sides by y. Let's separate this here. We're multiplying this both sides by y. Now if you multiply that both sides by y, you get dy dx, which is going to be equals to ln a y. But what is y? What is y? Let's start from where we started. What is y? Can you see what is y? Yeah. What are we getting here? We're getting dy dx equals to ln a to the power of x. What are we being told? What are we being told? Writing this is simple. Is you can say a power x multiplied by ln a. What am I differentiating? I'm differentiating this. What am I getting? I'm getting the same thing multiplied by ln of a. So then I can make a statement. It means that whenever I'm differentiating an exponential function a to the power x, that exponential function will bounce back like it happened with e, natural base. It will bounce back, but it will be multiplied by ln of the base. That's what it is. But what will happen if this function was x squared? Then it will multiply by ln of the base, multiplied by the derivative of argument like any other function. Let's do that. Let's do that as an example. Example. Remember I said to you, it's not that we're going to give you function like differentiate sine x, differentiate cos x. No, we're going to give you an exercise which combine the things which you've learned. In this case, once we've done this, we now be interested in looking at what is the derivative of 5 sine of x squared. That's what I'm interested in. But we are going to use this. And then we say the derivative here, the exponential function base 5 will bounce back exactly as it is. So it will be 5 sine x squared. But as a question of principle, whenever we differentiate, we must multiply by the derivative of argument. Then we multiply the derivative of this exponential function is cos, is sine. So the derivative will cos, retain that argument. Once we are differentiating sine here, it's a function, it has got an argument, we must multiply by the derivative of the argument. But because of what we have said here, we must multiply by the ln of the base. Are we together? Okay, let's see whether this agrees with what we saw before. If we had e to the power of x, we got the derivative as e to the power of x. But this is the same thing as e to the power of x multiplied by ln e. But what is ln e? It's 1. So then we don't write it there. So you see, this agrees with what we've already said. Are we together, guys? So look at what we've got from implicit differentiation. 2 bonuses without using the incremental condition. The derivative of a ln function, the derivative of exponential function any base a. That is that we've done there. So guys, I'm inviting you to learn these 2 things. At the moment, we're going to stop here. We know what the derivative of an exponential function any base a. It is always that function coming back multiplied by the derivative of the argument multiplied by the ln of the base. That will help you also when you go to integration. The knowledge of that is going to help you to see how to reverse the process of differentiation, which is exactly what we call integration. So please go and sit down, soak yourself in this, and make sure that you win. And thank you for listening. See you in the next presentation.